Last time you saw how every planet could kill you. This time, planets aren't enough. We're raising the stakes, much higher, because planets are just the beginning. Beyond them lie the most violent, unstable, and hostile environments the universe has to offer. Stars, black holes, neutron stars, colliding galaxies, places where survival isn't measured in minutes, but milliseconds. And we're starting close to home. You've only ever seen the sun from a safe distance. It's a familiar, life-giving star, a constant presence in our sky. But that friendly warmth is a carefully filtered illusion, a mere whisper of its true power. From about 150 million kilometers away, Earth is perfectly positioned in the habitable zone. Close enough to receive life-sustaining energy, but far enough to be shielded from the sun's most violent outbursts. Even from here, our atmosphere and magnetic field work over time, deflecting a constant storm of charged particles and blocking the most lethal forms of radiation. Without them, life on the surface would be impossible. And even with them, you still can't look at it for more than a second without damaging your eyes. Now, imagine we strip away that distance. Imagine getting close enough to see what it really is. Not a glowing circle in the sky, but a colossal nuclear furnace over 1 million kilometers wide, filling your entire field of view with roiling plasma and incandescent fire. This is a star in its raw, unfiltered glory. What we call the sun's surface is the photosphere, a churning layer of gas so dense that light can no longer pass through it. Above it lies the corona, a ghostly halo of plasma that is, paradoxically, hundreds of times hotter than the surface below, reaching millions of degrees. Humanity has sent a probe, the Parker Solar Probe, to touch the sun's corona, surviving this extreme environment through incredible engineering. But even this marvel of technology could never survive the photosphere. There's no way to land on the sun. It has no solid surface, only an endless, turbulent ocean of superheated plasma. So for a moment, let's suspend the laws of physics that would prevent you from ever getting here. Imagine you're placed directly onto the photosphere. Before you could even process your surroundings, you'd be hit by a radiation storm of unimaginable intensity. A torrent of gamma rays, X-rays, and charged particles would bombard you, shredding your DNA and destroying your cells on a molecular level. Simultaneously, the brightness alone, millions of times more intense than anything you've ever experienced, would overwhelm your optic nerves, causing instant and permanent blindness. Then comes the gravity. At nearly 30 times stronger than Earth's, it would feel like being crushed under the weight of a car. Your bones would fracture, your organs would rupture, the sheer force would be utterly insurmountable. And then, the heat. The sun's photosphere burns at over 5,500 degrees Celsius. That's hot enough to not just melt, but to boil the strongest materials known to science, like diamonds. Within fractions of a millisecond, any protective suit would fail catastrophically. Its materials would warp and liquefy. Your visor would melt away, then your skin, then everything else. Before your brain could even register the concept of pain, your entire body would be vaporized, its atoms torn apart and converted into a cloud of incandescent gas and plasma in a single, silent flash. You wouldn't burn. Burning is a chemical reaction, far too slow for this environment. You wouldn't scream. Sound can't travel in the near vacuum of the upper photosphere, and even if it could, you'd be gone before the impulse left your brain. You would simply and instantly stop existing. Now imagine drifting too close to a smaller, stellar mass black hole. From far away it looks calm, almost empty, but gravity here is absolute, and its gradient is steep. Long before you reach the point of no return, you'd cross a different threshold, the tidal radius. Here, the difference in gravitational pull between your head and your feet becomes a lethal force. Your feet, being closer, are pulled far more strongly than your head. This differential force would begin to stretch your body. You would be pulled, elongated, and simultaneously compressed from the sides. This process is called spaghettification. Your bones would crack, your organs would tear apart, and your body would be drawn out into a thin stream of plasma, all before you ever reached the event horizon. But a supermassive black hole is different. Its gravity is immensely powerful, but spread over a much larger area, making the tidal forces at its edge gentler. Here, you could cross the event horizon completely intact. That is, if you survive the journey. Most active black holes are surrounded by an accretion disk, a swirling vortex of gas, dust, and shredded stars, heated to millions of degrees. This disk unleashes a storm of high-energy radiation, from X-rays to gamma rays, that would sterilize your ship and you with it. But if you found a dormant one and crossed that invisible boundary, physics as we know it breaks down. This is the event horizon. To an outside observer, a strange thing happens. Your image would appear to slow down, your light shifting redder and redder, until you seem to freeze at the edge for eternity. A final, fading portrait. But for you, time wouldn't stop. In your frame of reference, you'd cross the horizon in an instant. Inside, all paths lead to one place, the singularity. The universe you knew would be gone, replaced by a warped reality where space and time have switched roles. You can no more stop moving toward the center than you can stop moving into the future. You'd keep falling, until the now inescapable tidal forces finally tear every atom of you apart, adding your fundamental particles to the infinite density at the heart of everything and nothing. If black holes are cosmic traps, neutron stars are cosmic crushers. Born from the explosive death of a massive star, they are the collapsed cores left behind. During the supernova, the core's gravity becomes so immense that it forces protons and electrons to merge into neutrons, a process called electron capture. The result is an object that is deceptively small, only about 20 kilometers wide, the size of a city. But it is so unimaginably dense, it packs the mass of 1.5 suns into that tiny space. A single teaspoon of neutron star material would weigh billions of tons on Earth, more than all of humanity combined. This density creates a gravitational field second only to a black hole. But unlike a black hole, a neutron star has a solid surface you could, in theory, get close to. And that's where the real nightmare begins. Many neutron stars are magnetars, possessing the most powerful magnetic fields in the universe. 1,000 trillion times stronger than Earth's. Their magnetic fields are catastrophic. Get within 1,000 kilometers, and this field would warp the atoms in your body. Your electronics would fail instantly. The very structure of your ship would be compromised. Then comes the radiation. Spinning hundreds of times per second, these stars, known as pulsars, sweep beams of lethal energy across space. These beams, intense X-rays and gamma rays, would tear through your body at the cellular level. Your skin would boil, your blood would vaporize, and if you somehow survived all that, gravity would do the rest. The star's immense gravitational pull creates extreme tidal forces. The gravity at your feet would be exponentially stronger than at your head, stretching your body into a thin strand of matter, a process gruesomely called spaghettification. You would be pulled apart, atom by atom. You wouldn't die as a person. You'd die as a stream of scattered particles, absorbed into the star's violent, chaotic dance. Now zoom out, far beyond stars and planets. Imagine flying into a region where thousands of galaxies are colliding. Gas is compressed. Radiation surges. Temperatures reach over 160 million degrees. At that heat, matter doesn't burn. It ionizes. The moment you crossed into this environment, shock waves traveling thousands of kilometers per second would rip your ship apart. Your body would be exposed to radiation hotter than the surface of stars. You would boil, vaporize, and disintegrate almost instantly. No warning, no escape. Finally, go back in time. Billions of years. You're near a massive star at the moment it dies. When it explodes, the brightness briefly outshines entire galaxies. Within milliseconds, neutrinos flood space, passing through your body and rupturing cells from the inside. Then the shock wave hits, moving faster than you can comprehend. Before your nerves fire, before pain exists, you are erased, your atoms scattered across space. From stars to black holes, from radiation to gravity, the universe is filled with places where survival isn't difficult. It's impossible. Earth isn't just home. It's a narrow exception in a universe built on destruction. And the real question isn't why these places would kill you. It's why this one doesn't.